Hi everybody, welcome back. So last time we were talking about what in the world is um, aerodynamics. And this time we're going to be moving onward and we'll be moving into what are those flow variables we were talking about. So going from what is aerodynamics to flow variables. So let's begin. Now, what are the flow variables we see in aerodynamics? So let's go through the common ones. Won't talk about the uncommon ones quite yet. And those would be things like velocity, pressure, viscosity, density, and temperature. Now, of these five, four of these are molecular in nature. So I'm talking about there is some sort of atomic structure, and that atomic structure is leading to those four properties. Velocity is not. Now, as we move through this course, we're going to realize is that when we're solving our equations, we're going to have various assumptions we're going to make. They're going to help make our equations more simple. And so I'm going to go ahead and write that over here. Let's see. Assumptions. There we go. Now, the first two that we're going to run into is what's called incompressible and inviscid. What does that mean? Well, don't worry about that too much yet because we're going to talk about that a lot later. But at its basic, if I can actually write, there we go. At basic, this is saying that my density is equal to a constant and my viscosity is equal to 0. We're going to get a lot of work out of those two. And you're like, wait a second, but didn't you say air was compressible? It is, but it's not compressing in all situations. In some situations, we can act as if it's incompressible and still get very accurate results. So in those cases, we would only care about velocity and pressure because the other ones are not going to come into play. Then we can have still incompressible flow, but now we also have viscous flow. So viscosity is now important because we're now saying our viscosity is not equal to 0. As a note, it's never equal to 0, but in some cases its effect is so small that it's negligible. Our density is still going to be constant. And then finally, we're really not making pretty much any assumptions. We can say that our flow is compressible, so density is actually changing as a function of position in the flow and time, and also our viscosity is not equal to 0. So that would be compressible. That looks more like gumpressible, compressible, and viscous. Now, I'd like to focus on the viscous ones right here, mostly because people kind of struggle to figure out why in the world does density and temperature come into play only at the end there. I mean, mostly because we were saying bringing compressible, but why is viscous going to suddenly bring into temperature? The reason that temperature is only shown in that last one, and even density is only shown in that last one, we bring in both compressibility and the viscous nature, is coming back to kind of our re-entry vehicle standard here. It's either for re-entry vehicles where it's going very, very fast, or if we have some extremely fast rocket or spacecraft or other sort of vehicle which has like shock waves coming over it. In those cases, the shock waves are where the compressibility and the viscous nature happens. And also, in a very, very small area, right next to the spacecraft's side. So if I do this, I have something called the boundary layer. And that it's very important to take into account viscosity there. There we go. And our boundary layer. So why shock waves and why the boundary layer? Well, boundary layer is simply where I go from having my free stream velocity right here to being a velocity of 0 at the surface. We have to have some sort of transition area, and that's the boundary layer. And viscosity is how we go from transitioning to one to the other, and it's where friction comes into play. Shock waves matter because across the shock wave, I have a sudden change in density and temperature and pressure. So density changes, temperature changes, and pressure changes, and depending on the strength of the shock wave, depends on how much these are changing. So it's all very, very important to tell what's going on in our flow. Now, for most of this course, we're going to be in the incompressible and inviscid. Okay, this is going to be a lot of the course. And we're not going to be really going into compressible flow all that much this semester. And the great thing is, by having incompressible and viscid assumptions, all of our equations that we're going to be learning about, the Navier-Stokes equations, other continuity equations, are much simpler. So that'll be very nice for us. Okay. We'll stop here for a moment and then we'll continue on next time.